person and also our guests online. I'm excited to present to you my PhD thesis on agile aerial autonomy. Human pilots are amazing in controlling drones at extreme speeds through difficult parcours in a sport called drone racing. It takes years of training, but finally they're capable of doing complex maneuvers in tight spaces and even overtaking opponents in challenging situations. But humans are not only very good at drone racing. Their skills also transferred to other environments, like industrial buildings. Imagine doing a 3D scan or an inspection task with this level of control and agility. Mission times will reduce to a fraction of what's possible today. If we can overcome the challenges in agile aerial autonomy, we can maximize utility, coverage, and robustness, and make modern applications more reliable and profitable. This can, for example, be used in agriculture, inspection, or even search and rescue. But for this, we need agile planning. Agile planning means that we can exploit the full actuator potential of our drones. Furthermore, we need agile control. Drones are an inherently unstable system, and if left uncontrolled, they simply fall out of the sky and crash. However, they present their own difficulties to agile flight because they are a nonlinear and underactuated system. Furthermore, in real-world applications, we have to deal with uncertainties, with model mismatch, and with complex aerodynamic effects. However, we also need onboard estimation. GPS has been around for decades, but it is relatively slow and noisy. And most importantly, GPS is not always available. For example, here indoors or underground, there is simply no signal. Luckily, there is visual inertial odometry, which gives us precise environment relative localization. But it also brings its own set of disadvantages. There is, for example, motion blur, which limits the quality, or high dynamic range seeds, or other visual deficiencies. So, what kind of drones are available today? There are many commercial drones, like first-person view drone for races, or the highly autonomous Skydio drone. But there are also many open-source research platforms, the small Crazy Fly, or the vision-based grasp pod. There are also highly autonomous solutions, like the ASL Flight from Professor Siegwart's school. Unfortunately, we notice a trend here. With a higher level of autonomy, vehicles typically become less agile. This is not only because autonomy requires a lot of compute resources, and this makes the drones big and heavier, but also because the autonomous system typically make conservative control margins, and they are not capable of exploiting the full actuator potential. The goal of my thesis is to raise the level of autonomy from where we are today to an unforeseen level. So what is required for agile flight? We can build on the three typical pillars of robotics. First, we have estimation, knowing where we are. Then we have planning, knowing what to do. And finally, there's control, knowing how to do it. We can lay out today's available components on a qualitative comparison by their compute requirements and their sensor, algorithmic, and modeling accuracy. We have, for example, the aforementioned GPS, which uses low computational power, but it also gives us relatively low accuracy. Still, it is used in many industrial applications. Sometimes, these industrial applications use no planning at all and do some simple set point scheduling. But more advanced applications use, for example, polynomial trajectory planning. This is super efficient, but it makes rough approximations of the platform. To control them, they typically use cascaded PID controllers or even LQ regulators. These are also efficient to run, but they make similar approximations of the system and are incapable of dealing with the true actuated limits. For localization nowadays, we have filtering and sliding window-based visual inertial odometry. This gives us very fast and environment-relative localization. With similar numerical methods, we can do model predictive control. This allows us to account for nonlinear systems and correctly include actuator saturations. If we want to deal with non-convex task formulations or multimodal noise, we need to switch to sampling-based methods. And here, typically, the compute requirements explode. Similar requirements are met by, for example, full bundle adjustment, visual inertial odometry, which can generate beautiful maps and recover precise estimates of the drone trajectory, but they do not run on light. The same goes for global trajectory optimization, which can plan over long time horizons or even complete missions, and often uses a lot of time to come up with solutions. In research, we also have motion capture systems for estimation. They are insanely precise and fast, but they require instrumented environments. And this means we can't use them to fly out in the wild. It is important to realize that not all of those systems run in real time. And furthermore, not all of the systems are accurate enough to perform agile flight. In this thesis, I will go through trajectory optimization to plan for static missions, execute them using model predictive controllers, and also see what implications this has for visual inertial odometry. To verify my planning algorithms, I will also make use of the motion capture system. So with this out of the way, we need a nice task to test our algorithms on. Interestingly, drone racing is an excellent stepping stone towards agile aerial autonomy. This is because it challenges all individual subsystems. The first subsystem I would like to look into is planning. So if you're planning for drone racing, we want to be fast. And if you want to win, we need to be time optimal. Time optimal means that a trajectory is the best a certain platform can achieve. Now, what limits us on our platforms? Well, if you look at the quadrotor can produce 4 thrusts. These thrusts, however, have to stay within specific margins. There is a specific upper bound and lower bound to the thrusts our actuators can produce. Now, if we want to be quick, we want maximum acceleration. What we want is acceleration in the right direction. So we need to rotate our drone around. And for this, we need some torque. Now, if we apply a torque through differential thrusts on the drone, we limit what we can get in terms of acceleration out of it. It is important to understand that because the quadrotor is an underactuated vehicle, its reachable acceleration and torque space is coupled. This means if we want maximum acceleration, we can exactly have 0 torque. And if we want the maximum torque, we get exactly half the maximum acceleration. Now, how can we plan time-optimal trajectories through a sequence of waypoints, which is actually what drone racing is? If we look at the existing methods, there are several state-of-the-art approaches we could use. For example, there are sampling-based approaches. However, if we want to capture the quadrotor dynamics on the level of the actuators so that we can correctly limit them, sampling complexity simply explodes, and this becomes computationally untractable. There is dynamic programming. However, subsections of our global optimal solutions unfortunately don't correspond to their local optims, and this renders dynamic programming ineffective. There are also bang-bang approximations, for example, on the acceleration space, but those are infeasible by the quadrotor dynamics. There have been approaches to bang-bang approaches to quadrotors on the thrust level, but these only work in 2D scenarios and in state-to-state transitions, but they don't work for general 3D multi-waypoint flight. Then we have the differential flatness-based polynomial trajectory planning. However, polynomials are inherently smooth, and this smoothness is not time optimal. They typically only allow state-to-state transitions, and they make it nearly impossible to apply the true actuator constraints. So all of those methods have some severe downsides, and this is where my contributions comes. To approach the problem of time-optimal planning, I use discretized trajectories. It means that we take a trajectory and split it in many small segments. We'll call them nodes. Between the nodes, we can enforce the dynamics of the drone and the actuator limitations. Now, if we want our trajectory to pass through multiple goals or multiple waypoints, we can assign them along the trajectory as constraints, but we have to assign them to specific nodes. Now, even though we can optimize the overall time, we have already fixed the fractional time spent between each waypoint. And this means that our solution will be suboptimal. So in my approach, instead of using waypoint allocation to specific nodes, I formulate the measure of progress, which is only allowed to change within proximity of a waypoint. What this means is that we have a measure of progress along our trajectory for each waypoint. And this measure of progress can only mark a waypoint as passed or check it off if the trajectory passes close enough to this waypoint. We do this by using complementary progress constraints. A complementary constraint is a constraint that consists of 2 factors. These 2 factors here have to equal 0 always. This means that at least one of the factor must be 0 at all times. For an example, if we are far away from a waypoint, our distance is greater than our tolerance, and the right factor here is non-zero. This means that our progress must be 0, and we cannot check off the waypoint at this time. However, if we get within a close distance of our waypoint, the distance minus the tolerance can become 0, and now our left-hand side factor, the progress, can be non-zero and mark this waypoint as completed. This allows simultaneous optimization of the trajectory itself and the waypoint time allocation. And this is the first method that actually allows it to plan time-optimal trajectories for quadrotors. Now, we verified this in real-world experiments that you can see here. We have pre-computed the trajectory and fly it with our drone in a large motion capture system. The drone flies through the parkour pretty quickly and using its full actuated potential. In fact, the drone is so fast that it beats human pilots. Now here it becomes interesting because we can compare humans to autonomous drones. If we plot the acceleration here in yellow to red on the left-hand side for the human and on the right-hand side for our autonomous approach, we can not only see that our autonomous approach is much more consistent, but also that the human has these very yellow cold spots on the trajectory. These are the spots where the human does not use the full actuation, does not use the full potential of the drone. And these are the spots where the human falls behind our autonomous algorithm. We can see this reflected in the lab timings that we achieve. Our autonomous system is not only much more consistent in the timing it achieves, but it also beats the human by over half a second. So with this research, we have shown that computing time-optimal trajectories for quadrotors is in fact possible. They are feasible, and we have verified them in real-world flights, and they beat human pilots and are more consistent. Finally, we can now use these trajectories as baselines for new approaches. For example, model predictive control that tries to do the same thing in real time, sampling-based approaches to also include obstacle avoidance, or learning-based approaches to find more efficient formulations. However, we have not yet verified these trajectories for global optimality because these are a very complicated non-convex system. But we also haven't found a counterexample yet. So how do we execute those trajectories? I want now to lead over into the topic of control. Model predictive control is a natural fit for quadrotas. Its versatile reference and objective formulations allow us to use the same controller to achieve different goals. We can do smooth state-to-state transitions, follow high-level velocity commands, or track a sample trajectory. We can also include analytical trajectory formulations. Furthermore, its predictive nature allows it to anticipate what's coming up on a trajectory, and it gives us multiple measures of errors that we can trade off against each other. With this, we can compromise between fast reactive flight or smooth flight. Smoothness will become more important if we look towards onboard sensors just in a moment. Furthermore, model predictive control can correctly account for the nonlinear system dynamics, and it allows us to include the true actuated saturations. This is important for agile flight, but not only there. Imagine you have a drone flying up high in the sky, and one motor fails. Now the drone loses 1 degree of freedom, and it starts to spin. Most controllers are incapable in dealing with this situation. The model predictive control can use actuated constraint formulation to realize that there is no more thrust on the motor. It then exploits the nonlinear dynamics to control the spin of the drone and bring it back into a safe flight state. We tested this in real world in an agile maneuver like this flip, where on top, one actuator is disabled. The drone starts to spin, but the controller can capture it and bring it back into a safe flight. Now, if we want to do agile maneuvers, we also need precise state estimation. And for this, we need high quality sensor machines. However, if we want to go anywhere, we have to bring our own sensors and have them on board. Mounting them fixed to the quadrotor implies that now actions of the quadrotor affect its perception. For a camera, this can mean that a quick rotation introduces a lot of motion blur or large viewpoint changes, which make it difficult to get high quality estimates out of the images. Furthermore, if we do something simple like position control, there is 1 degree of freedom in the yaw that's left open. For object tracking or cinematography, we need to control the motion of the vehicle together with its orientation. MPC allows us to couple perception and action objectives. We can do so by including the camera projection into the model of the MPC. This allows us to optimize for reduced motion blur or maximize the visibility of an object. We have used this in multiple publications, one of which you see here. Here the drone is tasked with flying through a series of gates, and these gates are actually detected by a neural network. However, to be able to do so, we need to guarantee that we can always look at the next upcoming gate. The MPC controls that and makes sure we always have the gate in view. Furthermore, you see now my colleagues moving these gates around. The MPC can use updated knowledge about the gates to quickly generate new trajectories